Good morning. Today, I'd like to talk some about issues that are related to things that we have previously talked about and make an abbreviation which is, at this point of time, mildly misleading. We've previously seen that you can write a complex number in a plus bi form, or you can also write it this way. A complex number, z1, can be written as the modulus of that number times cosine theta 1 plus I sine theta 1, where theta 1 is the angle that the line segment from the origin to the complex number z1 makes with the positive x-axis. In a similar way, z2 is the modulus of z2 times the cosine of angle plus I sine of angle, with the angle theta 2 being the angle that goes with z number 2. I like to multiply these two things together in this form and see if I can gain any insight. I've rearranged the order in which some of these things get multiplied. This is justified by our arguments involving the bracket quantities. I've also grouped together the cosine plus I sine quantities. This is justified because of the properties of the bracket quantities. I'll multiply these quantities out in the usual way, which once again is logically justified by the bracket game that we played. In what results, I'll have a real number, cosine theta 1 times cosine theta 2 minus sine theta 1 sine theta 2 plus this I quantity times the real number cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2. If you'll remember your trigonometry, we have trig identities for both of those things that we're looking at. This quantity is cosine of theta 1 plus theta 2, and this quantity is sine of theta 1 plus theta 2. So if I multiply two complex numbers together, I can instantaneously write it in this cosine sine type form. The modulus of z1, z2 is modulus of z1 times modulus of z2 times the modulus of that, which is 1. The modulus of z1, z2 is the product of the two moduli separately. The theta quantity is often called the argument of the complex number. Looking at my result, the argument of z1, z2 is the sum of the arguments for z1 and z2 separately. So I have two different types of behavior going on here. On the one hand, I've got things multiplying together to give me the corresponding characteristic of the z1, z2 quantity, and on the other, I have things added together. This is very suggestive. This should remind us of something. In the ordinary real numbers, if I have a constant times e raised to a power and multiply that by a constant times e raised to another power, the result is a constant times an exponential value. The constant is a times b, just like the product of our two moduli, and the quantity that e gets raised to is the sum of the quantities to which e was raised to separately. It's worth mentioning that this is true for e to a power, but it's also true if it was a times 5 to the alpha times b times 5 to the beta. That would be a power of 5, alpha plus beta. So On one level, I maybe shouldn't take this specific base E very seriously. I'm going to define a symbol. This symbol is going to have an E in it, which, in view of our comment just a moment ago, I shouldn't take too seriously. I do not know that this represents 2.71 some odd at this moment, but I'm going to define the symbol e raised to the a plus bi power to be the following thing. It will be the real number, e to the a, multiplied by that symbol, which I'm going to make up a definition for this symbol. And once again, you shouldn't take that e too seriously at the moment, although later on we will take it seriously. For now, this symbol is just shorthand for cosine b plus I sine b. Up to that level of vagueness, a complex number is its modulus, which is a real number, a non-negative real number, times this symbol, which is shorthand for cosine of theta plus I sine theta. We've already figured out something about how to do multiplication. If I write it in this symbolism, which, to continue emphasizing, at the moment is just a symbol, I don't know that e is 2.7 some odd. If I write out my multiplication fact using this symbolism, it'll be very suggestive to me. If I have two complex numbers and I just multiply them together, we've already figured out that z1, z2 is modulus z1 modulus z2 times the quantity cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2, which in our new symbolism, we're writing in this way. If you compare this to that, basically all we're saying is if you use a symbolism like this, it represents how to do the multiplication in a very compact form. It's interesting to look at powers of a complex variable. So I'm going to suppose I have some z which is equal to its modulus times this symbol e to the I theta, where theta is our familiar angle. We now know how to manipulate these things in terms of multiplication as though it was just ordinary algebra. If I calculate z squared in the obvious way, the modulus is the square of the modulus of z. E to the I theta times e to the I theta is e to the I times 2 theta. Z cubed is z times z squared. We've already figured out what z squared is, though, so applying the same sort of arithmetic that we have now, we found out that z cubed is the cube of the modulus of z times e raised to the I times 3 theta, although I don't really know that that's e, and I don't really know it's a power yet. If I calculate z raised to the 4th power, what I get is exactly what I'm beginning to suspect that I should get. I really should do a proof by way of mathematical induction on this, but I'm not going to. Suppose that n is a positive integer, like 2 or 3 or 4. I claim it should be fairly obvious what z raised to the n power is. At this stage, it's worth mentioning that there is a little bit of wiggle room when we figure out what the theta is for a complex number. If I had a certain theta value, I could add any multiple of 2 pi radians or any multiple of 360 degrees, and my location would be the same. So when I have this, I could also have that theta plus 2 pi radians, theta plus 360 degrees, or I could have that theta plus 4 pi, or theta plus 720 degrees, and so on. There's actually an unlimited number of theta values that I could have, but if we have any sense, we'll use the smallest one that we can get away with. That's going to have consequences for what I'm about to say. When I calculate z to a power, I take the modulus to that power, then e to the I, an angle that will work for z, and the power. If a is a positive real number, we say principal square root of a is a to the 1/2 power. The principal cube root of a is a to the 1/3 power, and more generally, the principal nth root of a is a raised to the 1 over n power. I'm going to make an analogy between this and these positive whole number powers that we have here, with the understanding that I can alter theta by adding a multiple of a full circle to it. So instead of raising things to the n power, I'm going to raise them to the 1 over n power. I'm going to think of nth roots of complex number z as having modulus principal nth root of the length of the complex number times one of these e to a power symbols, theta plus 2 pi radians times m, where m is a whole number, has the same terminal point as just theta. So I can think of m as being 0 and 1 and 2 and so on. If there wasn't the division by n, that would be landing me at the same place constantly. The n on the bottom of the fraction is going to change that. Before I start calculating anything, I do want to verify that this is going to work out the way that we think it should. So if I take one of these quantities of interest and raise it to the n power, properties that we have already figured out tell us that this is going to be the nth power of the nth root of the modulus of z, and because of the way the e to a symbol connected to multiplying cosine of thetas plus I sine thetas, we know that it's okay to write this as that. So I cancel the n's out. Now, this looks like it's not right, but remember the definition of this e to the I times something symbol is cosine of the something plus I sine of the something. So I can write it in this format. Cosine and sine both have period 2 pi, so this angle is theta plus a whole number of full circles that has the same terminal point as theta did. Cosine of this is cosine theta, and likewise for sine. So this tells me if I take one of the quantities that looks like this and raise it to the n power, what I end up with is modulus of z times cosine theta plus I sine theta, which in our other language was modulus of z symbol ei theta, which was z. If I raise any quantity of this type to the n power, I get z. At first glance, it might seem like you're going to get an infinite number of cube roots, for instance. That doesn't turn out to be the case, as we're going to see in an example. So let's find all cube roots of z equal 1 plus I. I'm writing this as 1 plus 1 with a little underscore I to keep straight where the numbers are coming from. The modulus of z is the square root of the real part, that 1, squared. The imaginary part is the coefficient of the I. It's the 1 with the little line underneath of it. Modulus of z is radical 1 squared plus 1 squared, which is radical 2. The angle that the complex number makes with the positive x-axis is 45 degrees, pi over 4 if you prefer radians. Cube roots should look like this. I should have the cube root of the modulus of z, the cube root of the square root of 2, that'll be the sixth root of 2, multiplied by one of these cosine plus I sine things. Because of the periodicity that we mentioned previously, I'll have pi over 4 plus 2 pi times an integer divided by 3. And as mentioned previously, it looks like there's going to be an unlimited supply of cube roots, but that'll turn out not to be true. Thinking of starting with m equals 0, let's think about what these things that I'm feeding into the sine and cosine are going to be for various values of m. That is, think about the argument of the complex number. Starting with m equals 0, I want to look at consecutive m values and see what kind of things I get. Before I do that, though, I want to simplify the thing that I'm feeding into the sine and cosine and look at its values separately. Looking at m equals 0, 1, 2, and 3, it looks like we're going to be able to get, if we continued with m equal 4, 5, 6, 7, and so on, an unlimited supply of arguments to feed into the complex number. That turns out not to be true, though. I've left these in unreduced form just to check on something. This is the one that I would get if I wasn't concerned about that whole add a full circle thing. This is the argument that I get if I add in one full circle, two full circles, three full circles. I'm going to want to look at that last one, the m equal 3, in some detail because it's extremely informative. The m equals 3 argument, 25 pi over 12, is pi over 12 plus 24 pi over 12. This is pi over 12 plus 2 pi. The angle that we would be thinking of is coterminal with angle pi over 12. So this m equal 3 gives us the same position that we had at m equals 0. And then we're just going to get repetitions of things we've already seen. So it's not necessary to look at all possible values of m, only 0, 1, and 2. That'll tell us all of the interesting bits. It's worth mentioning that this angle is 8 pi over 12 bigger than that one. If I take this angle and add 8 pi over 12 to it, I get 17 pi over 12. So I have some angle. It gets bigger by a certain amount when I look at that one. And then when I look at that one, and then this one, it gets bigger by that same amount, 8 pi over 12. In terms of the angular position of these complex roots, they're going to be evenly spaced, which we might have suspected from when we looked at the cube roots of unity. I've put my calculator in complex number mode. I've put in the sixth root of 2 times cosine pi over 12 plus I sine pi over 12 with the resulting expression. Let me raise that to the third power, and I get 1 plus 1i. I've set the number of digits displayed to 5 or 6 so that I don't see the rounding errors. I've put in the same complex number, except this time the argument, the angle, is 9 pi divided by 12. I'll see what the cube of this number is. It would be 1 plus 1i. Here, I've changed the argument to 17 pi over 12, and we'll cube that, but we already know what we're going to get. 1 plus 1i. So in this way, I can calculate the 3 cube roots of any non-zero complex number, or more generally, any nth root of any complex number. This is an informal description of what's called De Moivre's theorem. We'll talk more about that at another date. For the last time in this video, though, I do want to emphasize that the symbolism e raised to a power with an I in it as being interpreted as cosine of the quantity plus I sine of the quantity is still fairly arbitrary. It doesn't necessarily, at this stage, have anything whatsoever to do with our familiar E from exponential growth or radioactive decay. It's going to turn out, though, that it does, but we can't see that until we know certain other things. So we're going to have to talk some about functions, limits, continuity, derivatives. Once we know that, we'll be able to basically do everything with power series that we did back in second semester calculus. In second semester calculus, that was a topic that didn't occupy a huge amount of our time. It's going to turn out now, in this setting, functions of a complex variable. This business about power series turns out to be of crucial importance. So this is down the road. In the meantime, I hope everybody has a good night. I'll talk to you again soon.